Hello and welcome back. Performance of applications remains an important and critical area to address across the enterprises. In this lecture, we will look at some of the properties of cloud-based platforms which have an important impact on the performance of applications and software systems that you build and deploy on cloud-based platforms. Let us start by looking at what do we mean by performance in our particular case. Performance of a system, of a software system, is often characterized by the quantum of useful work that is done by the system for a given amount of time and computing resources. And often it is measured by looking at some of the metrics such as response time, which should be smaller for a better performance, and latency. For provisioning computing resources, you should have minimum latency, for example. So the smaller latency is better. And latency could also be in the communication time that it takes from going from one machine to another, let's say. And throughput, that is the rate of processing the work. The faster you process, you get better throughput. That is, you can do more work per unit of time. And similarly, the resource utilization. That is, how efficiently do you utilize the computing resources. Often when you build a software application, requirements with respect to the performance of a system are typically specified, and that falls in the non-functional requirements category. For example, let's say if you are building a web-based application, you may be required to support where they say that average web page of the served by the application should load within less than 3 seconds, and it should be able to process a workload of 1000 concurrent users, and the maximum amount of memory consumed by the web application on a server side should be less than, let's say, 1 gigabyte. And the CPU utilization on that server-side machine where, let's say, your database component of the application solution is hosted, that should remain less than, let's say, 30%. And there may be other metrics which will be specified as the performance requirements from that application. So when you design that kind of an application, you need to implement certain tactics, certain features in a specific manner so as to achieve the specified level of performance by your application. Now, your platform on which you build your application or on which you deploy your application, all the APIs and other components that you use to build an application will have an impact on how much performance you can extract and build into the software that you are trying to design and architect. So from that standpoint, it is important to understand key characteristics and properties of the platform that you are using to build and deploy your application. So just to reiterate, achieving better performance, what you should do, your system should do more work at a faster rate and by consuming minimum amount of computing resources. And as usual, the time-proven techniques and design principle which have held good on a non-cloud platform, they apply on a cloud platform as well. For example, you should try to exploit parallelism, and you can use pooling of shared resources, and you can minimize the round trip between different tiers of the application, and also try to put the processing logic near the data or the resources that it needs, right? And there are several other performance related best practices and principles which you can use when you design and architect your solutions. So all of these best practices, which are known from the time prior to the cloud platforms came into existence, they all continue to apply. However, there will still be certain specific points which these modern platforms like cloud and virtualization based platforms, they bring with them. And we'll look at some of those points which you as a designer, as an architect of different software applications would like to exploit, or you would have to worry about those, address those or mitigate those points so as to achieve better performance for your applications. So some of the key points that apply to cloud-based platforms is, first is that there is a consolidation of computing resources that happens in the data centers. And the idea here is that the enterprises wants to, if you have adopted the cloud platforms in your enterprise, for example, you may have set up a private cloud, and the idea there is that you want to improve the utilization of your data center. So at an enterprise level, that is a performance improvement if you're looking at just the utilization across all the application. And you use virtualization technologies to achieve this. And when it comes to the individual applications, rapid elasticity that comes with cloud platforms, that helps to achieve better performance, because you can now provision different computing resources on demand, and it will allow you, as we'll see in subsequent files, to do faster scaling. And similarly, multi-tenancy may have some negative impacts at times. We'll see more details on this as well. So these are some of the high-level key points which you should consider while building applications for a cloud-based platform. So let's look at elasticity slightly in more detail. What it means is that the computing resources that you provision, that you obtain on a cloud-based platform, they are elastic in nature. That is, you can increase them by using programmatic means on demand by all your applications. And there may be facilities available on different cloud platforms where you can specify certain rules such that depending upon the need, computing resources could be provisioned automatically. For example, you may have the ability to specify a rule which says that when the CPU usage, let's say, on a virtual machine that is hosting your web application server reaches above 80% for let's say 10 or 15 minutes, you want to launch a new virtual machine so that some of the load, assuming that such a spike in CPU usage was caused by some increased load in the requests that your application is handling, if that is what it indicates, then you would want to launch a new virtual machine and start a newer instance of the application server. And your solution should be designed in such a manner that you are able to load balance requests automatically with a newer virtual machine as well. So in that sense, you are able to do some sort of a horizontal scaling of your web application server. And since on a cloud-based platform, this kind of provisioning is programmatic and is done automatically, so you have eliminated, you don't have any dependency on manual intervention for any kind of provisioning of such resources. But again, doing this kind of automatic scaling still remains a matter of research. How do you determine that when do you have to really start a new virtual machine, for example? You have to have a appropriate mechanism built into your solution so that you can determine the right events, the right moments in time when to scale up or scale down. Because the whole idea here is that you want to optimize the utilization of your computing resources, at the same time trying to address the performance needs in terms of, let's say, response time or handling of a particular load of requests to meet certain quality of service requirements from your application. Now, provisioning latency remains an important issue, particularly when you're looking at infrastructure as a service kind of clouds. For example, if you look at Amazon Web Services, they have different types of virtual machine instance configurations. You may have a small instance which comprises of some amount of compute units and some amount of main memory and hard disk, etc. And similarly, you have other instances such as large, which differs in terms of how many compute units it comprises of and how much of main memory it has. By one study, which is even though slightly dated, but still the point I'm trying to highlight here is that there is some amount of delay or the latency which you will experience from the time you request the launch of the virtual machine till the time that machine is becoming available for you to serve the actual requests. Now, being aware of this latency is an important point when you're trying to do auto scaling or trying to set up some mechanism wherein you have to request additional resources, additional virtual machines at a right moment in time, so that you do not lose any requests or you do not have degradation in the quality of service of your applications which are deployed on such virtual machines. So from that standpoint, it is important that you know these latencies and you know how they vary with the size of virtual machines and so on. So how do you address the provisioning latency issues? So what you need to do is basically develop some strategy to forecast the number of resources that you need for the optimal operation of your application services. So basic idea there is that you need to determine the events that may indicate some potential surge in the load on your application. And then based on that, you calculate the amount of additional resources that you need to handle such a load. Basically, how much you can succeed in optimizing the addition or the scaling by using this idea depends on whether you are picking the right events that really indicate the load surge and accuracy in your calculating the resource needs. Now, what could be the right events? Let's talk a little bit about that. It could be as simple as just an indication of some particular resource being consumed at a certain level for a long enough period. For example, you can watch for CPU usage. If it remains above, let's say, 90% for 10 or 15 minutes, it might indicate that there is some heavy load being experienced by the application. Or similarly, it could be your memory consumption, for example, right? Alternatively, you may also want to build certain other instrumentation which monitor some application specific patterns. For example, you might want to monitor the transactions which are being submitted into your application. For example, let's say if it is the case of a application which is implementing some online chat session kind of a functionality, then you may just want to watch for the number of users, let's say. So a large enough number of users might also indicate that your load is increasing. So the point that I'm trying to make is that usually you will have two types of events. One could be simply monitoring the resource indicators like CPU or memory usage, etc. Or you could also have to design more monitoring in your application itself to watch for application logic specific indicators which might suggest that the load experienced by the application is increasing, so that you can take timely decisions to add more resources and prevent any degradation in service. Now let's look at another issue, which is multi-tenancy. Cloud is a multi-tenant environment, and you may have different customers' applications and data hosted on a shared infrastructure. For instance, in a case of infrastructure as a service, you may have a single physical disk, let's say, holding data from different consumers, or a single physical host may be running virtual machines from different consumers, which may have deployed different types of applications, which may be having different resource consumption patterns and so on. And why do you need this kind of a setup is typically from the cloud vendor standpoint, they need to optimize the resource utilization so that a cloud vendor, a cloud provider can leverage the economies of scale and pass the benefits to the consumers. And consumers will assume that they are sandboxed in the sense that they can assume that their applications and data, they run in an isolated manner, in an isolated environment where they don't see any impact from the co-located virtual machines, let's say. So that is multi-tenancy, and let's look at what could it lead to in terms of performance. So this is how it could look like. So you may have a shared underlying physical host infrastructure where you have the physical resources and operating system and other features. And then you will have your virtual machine deployed on top of it. We have already seen this diagram where it says that you can have different virtual machines of belonging to different customers, and they may be running different types of loads. Now, major issue could be the performance interference. That is, one particular virtual machine may be running a type of load which can impact the performance of the co-located virtual machine. For example, it may be possible for someone to write an application or some piece of code where you are forcing the cache invalidation on the host CPU, and building the cache lines is kind of an expensive operation, and if your application is such that it is constantly forcing to evict the cache, then obviously it is going to have an adverse performance impact on the co-located virtual machines, because end of the day underlying physical infrastructure is still shared. So you need to be aware of these kind of interferences, and we'll look slightly more details on how you can measure this performance interference and then devise appropriate scheduling and deployment policies which you can apply to which you can use to determine how and where you should deploy your virtual machines. And as a cloud vendor, as a cloud provider, it is important for you to understand all these. And yet another thing related is the potential for one VM breaking into another. So there could be bugs in the virtual machine software, virtualization software, which could lead to the breaking of isolation. And from the security standpoint, of course, you can handle these things by appropriately protecting your data by encrypting it. But if you're looking at purely the performance aspect of it, then the compromising of one virtual machine may lead to, let's say, denial of service kind of a situation, where from the end user standpoint, your performance has degraded because the virtual machine now is unavailable and your requests from different users may not be able to be served. So how do you measure interference? One simple thing is, let's say if you are trying to set up a private cloud, or if you are a cloud vendor for that matter, you need to devise the policies which should guide you in your VM scheduling and VM deployment decisions. That is, how should you deploy different virtual machines on a given physical host so that there is a minimum interference in terms of performance. And the first thing to do when you put together this kind of performance interference measuring setup, you need to first model that what are different types of load combinations, workload combinations that are possible for all your applications that you are going to deploy on different virtual machines. So often you will have workload types which can be, let's say, IO intensive, or you can have, let's say, CPU intensive, or it can be some sort of a mixed load type, which could be a combination of the above two. Then you can try to set up two virtual machines on the single physical host and try to subject each one of those with some kind of a request load. Let's say you will be subjecting one of the virtual machines to a fixed request load of, let's say, 100 requests per second, whereas for the second VM you are subjecting it to a varying load, which, let's say, start with 100 requests per second and varies up to, let's say, 100,000 requests per second. And then you can see as the request load increases on the second one, how does the performance of the first one varies. So you can watch for various resource consumption on the virtual machine, and then based on that you will be able to determine the level of interference for various types of performance metrics. For example, CPU consumption, memory consumption, response time, or even throughput. So we did this kind of experiment across different virtualization types and different workload types. Some of the results I just want to highlight. So here we were using different types of virtualization. For example, LXC is a operating system based virtualization solution. You have VirtualBox from Oracle and XCN, Citrix XCN, and the native platform, that is no virtualization. So if you look at, there are different types of workload scenarios here. So each of this on the x-axis here, on the horizontal axis, each entry is a tuple which says on the first VM what is the predominant load type, and what is the predominant load type on the second VM is indicated by the second element of the tuple. So the first entry is CPU, which means the steady load type virtual machine has a CPU intensive load, and the second virtual machine on which we are increasing the load steadily has also a CPU intensive load. And similarly on the second one, a database engine is representing a mixed type of load, mix of IO intensiveness and CPU intensiveness, and so on. And then we are trying to measure the correlation here, correlation for the performance metrics of throughput. That is, we are trying to measure that as the load on the second virtual machine increases, how does the throughput get impacted on the other virtual machine. So interesting things here to note are few of these which I have highlighted. So interesting cases when you have a combination of CPU to IO intensiveness, and similarly for the case of DB, that is mixed load and IO intensive, and IO intensive for both. So we see there is some sort of interference here, and in this case we are looking at the negative correlation, which is a bad thing. Negative correlation means that when one quantity is increasing, the other tends to decrease. That is a negative correlation between two variables, two quantities. So what is happening here is, in these scenarios we are seeing negative correlation. Means that for this type of virtualization, LXC and native, when the workload combination of virtual machines is like this, we see a negative impact on the throughput. That is, throughput is negatively impacted. And similarly in case of IO intensive scenario. So in this fashion, you can see by subjecting your virtual machine to different types of workloads, and by deploying different types of workload on your virtual machines and then subjecting them to varying types of requests, varying load of requests, and then see how a particular performance indicator, performance matrix behaves. And similarly, if you look at the CPU consumption, so here also we have different types of performance interference. So if you see, in some cases we have a positive correlation, which is a bad scenario here, and I'm highlighting all of these. What it is trying to indicate here, for example, is that in case of a co-location scenario where one virtual machine is having a workload of CPU intensive type and another virtual machine is having IO intensive workload, and if you are using a hosted virtualization layer like VirtualBox, for example, then you are having a positive correlation for your CPU consumption. That is, the CPU consumption on a virtual machine which is subjected to a steady load tends to increase as the request load on the second virtual machine increases. And ideally you should not notice, you do not want to notice any change in CPU consumption when somebody else's workload is increasing, right? And similarly, you can interpret rest of the other readings. And another aspect that is interesting is, in certain cases you are seeing something which is useful. Here you see some negative correlation, which is good for us. And it all depends on the type of virtualization technology that you are using and the workload scenario. Because for example, in certain cases, the workload may be such that there is enough cache built up, which automatically helps the co-located virtual machine as well. So in that sense, it can act in your favor as well. But the point that I'm trying to stress out is that you have to be aware of such scenarios, that in what kind of scenarios it is helpful and in what kind of scenarios it acts against you, and what are the virtualization dependencies on it. That is, on what type of virtualization platform you will get what type of interference, good or bad. And the similar is the scenario here for memory. Okay, so let us summarize what we have seen so far in this lecture. So what we saw is that performance best practices from the good old non-cloud environments continue to apply on cloud as well. That is, you will still be using all the best practices like reducing the round trips and putting the data and the processing logic close by and making use of resource pooling and so on. So all those practices will still hold good when you develop and deploy applications for cloud platforms as well. However, cloud platforms bring certain characteristics which you can leverage to provide better performance on your applications. One of the key thing is that the resource elasticity, the computing resources elasticity which is available to you on a cloud-based platform, that can help you quickly scale your applications. You can add resources on demand and all in a programmatic manner. So your application senses the load and automatically tries to add at the right time more resources, or tries to reduce the resources when they are not needed. So overall you can scale easily, and you can also optimize on the resource utilization. And the virtual nature of resources is the key thing here, that is enabling the elasticity and on-demand provisioning. But performance remains again a design issue on cloud as well. What it means is that you as an architect has to design the performance into the application. Merely deploying a piece of software on cloud in itself is not going to make it better performant. So in that sense, it still remains an architect's responsibility to design performance into your application by leveraging all the available characteristics and features on the modern platforms like cloud. So that's pretty much it for this lecture. Thank you.